Okay, so one more tutorial on a question you guys posed from the questions in the first video on evolution of life and how it evolves. You guys posted a whole bunch of different ideas about questions about like, well, how does that work? Or I need more information about this. And this particular one, video is about chaos. And I wanted to use an example for mathematical description of chaos. And it's a behavior of a system, yeah? And it's where you move from predictable to unpredictable, but still functioning, not into a collapse situation. So what I'm going to do is show you a simulation of population growth that you can do. I'll post this on the Canvas page as well, which demonstrates that as the rate of change increases, a system moves from stable and predictable, very ordered. As you increase that rate of change, it becomes less predictable and then chaotic just before it collapses at a very high rate of change. So let me share my screen with you again, as always, and now we'll take a look at that system. So this is an Excel spreadsheet. I've programmed it here. R is the rate of change in a population. This would be like a population growth equation. I seed each one with the same number. And what these represent, these numbers, which are all proportions, right? This is 0.02 as a proportion, 0.49, 0.5 would be 50%, right? 1/2. What I've done is set these populations up to simulate 100% is the number, if you have the maximum number of individuals in a population that the environment can support, right? So if there's no number of individuals, but it's more like a percent of individuals that the environment can support. Every environment has a carrying capacity based upon a limiting resource. So some resource is limiting, and that tells you how many individuals you can support in that environment. The limiting part is called the carrying capacity, which is often they use the term K, the letter K, to represent that. The carrying capacity is the number of individuals that an environment can support. In our simulation here, that will be 1, right? 100% of the individuals. So you can see, what I did simply to program this was I took the number of individuals here, and in the next formula box, I multiply that times that the growth rate, R, which is at the very top, R equals 2 in this case. So B2, the cell B2, 0.02 times 2 gives us the maximum growth rate. And then I multiply that times 1 minus B2, 1 being the maximum number of individuals that can be maintained in the population. And then B2 is where we're at on the scale, like how close are we to that? So this allows the population to grow up to get near that, or as it turns out, you'll see it, we can kind of exceed that or whatever. Anyway, so if you grow slowly at R equals 2, you'll notice in this graph that we obtain this sort of stable level at 50%, and then we just stay there. Right? It's just like perfect, right? We approach the carrying capacity and then stay there. If you grow a little faster, R equals 3, you can see in this diagram, in the graph of this over here, you have this oscillation around that, around a stable point. This is more complex, a system, yet still predictable. Given where you're at, it oscillates in a predictable manner. If you look at R equals 3.4, we're still at a stable level. When you increase the growth rate to 3.7, you can see here that it becomes not predictable. So when we transition from predictable to not predictable, we enter the realm of chaos. Yeah, this is a chaotic system. It's still stable. That is, it's not crashing to zero. We're not destroying this system. It's a sustainable system. It's just not predictable. And that's what really chaos is. And systems tend to move towards this. Now, why? I don't know. That would be like saying, why does entropy increase in a system over time? Why is that? Why is the second law of thermodynamics real? I don't know. But this is also true. Systems will move towards this. And you can see as we move up 3.8, it becomes even less predictable, but still reasonably stable. At 4, it's getting close to where it crashes once in a while, but it still recovers. So this is like the maximum rate of change in this system that you can occupy without crashing. And then here at 4.2, we crashed. Yeah. So all of these unpredictable, but this one at 4.2, the growth rate's so fast that it guarantees at some point it will crash. So this is the edge of chaos is right between 4 and 4.2 for this system. And nature will maintain it in that place unless something weird happens. And that can occur. Just to give you some other ideas, I graphed the strange attractor for these systems at each growth rate. And I know strange attractor sounds like a lot of fun, like science fiction or something, but it's actually really simple. What you're doing is removing time from the graph. So I've taken the column of numbers, and then the next column of numbers, I shift down one, so that each XY point is the value at time t, and the y is the value at time t plus 1. Yeah. So I'm graphing, the incremental different changes in the system. And so when the growth rate's slow, it goes right up to 0.5 here and then stays point forever. Perfectly ordered system, super low entropy, right? A system that you can predict 100% of the time with absolute probability. That is the most ordered system you can have. Here's where the second law of thermodynamics comes into chaos, right? So this is ordered. If in a system, the second law of thermodynamics determines that entropy must increase over time, then we move up, yeah? So we increase the rate of change, and now it becomes less predictable. Still, the strange attractor, you notice you grow into this shape, this attractor shape, and then you just bounce around in there. It's not predictable, right? It's truly a chaotic system. You can't tell where it's going to be, but it's going to be somewhere on that attractor, right? It's not going to be over here somewhere. So it's a defined shape of a system, and it's chaotic, right? You can't quite predict what's going on, but it's bouncing around inside there. When you grow a little further, a little faster, here we are at the edge of chaos, you can see it, the attractor gets bigger, more complicated, less predictable, and you can see right down here in this iteration, it almost hits 0. Whoa, and then it pops back in. And maybe if you ran it, I could have run it out more time, eventually it may have collapsed, maybe not. Maybe the true edge of chaos is 3.9. I'd have to do that simulation. But anyways, once you obtain this, you notice that the strange attractors get bigger and more complex. And you're pushing that second law of thermodynamics, maximizing entropy before collapse. And so that's what chaos is about. Chaos is the math that describes a system maximizing its entropy, but not going beyond. All systems have constraints. In this case, it's the carrying capacity, right? So other systems have other physical constraints. So you can't grow forever. You can't grow, super fast. Or this is about rate of change. So think about mutation rates. If your mutation rates increase to some point, then you can, you just collapse. You don't live anymore because you're so variable that you can't, live in an environment. Your physiology collapses. But you can maximize a mutation rate, which will maximize the evolutionary rate, which maximizes the diversity in that system. So you can apply this to any rates of change, population growth, mutation rate, any of that sort of thing. Anyways, but that's how chaos relates to entropy, right? A predictable system, low entropy, will move towards maximum entropy before it collapses. And that's how nature works. So anyways, I hope that's helpful. I'll post this spreadsheet. You can play around with some chaos if you like. It's pretty fun. Anyhow, I hope that helps. See you soon.